All right, thanks for taking your lunch in here to talk about web application performance. Everyone's favorite lunchtime conversation, I know. So I'm John Riviello. I'm a web developer working for Comcast right now out of Philadelphia. And as you can see, I'm going to be talking about web application performance. This talk is based on some work I've done over the past year and a half or so on a product known as X2 Cloud TV. It's currently in a market trial, and we're slowly rolling it out across the country. And specifically, it's about what we learned about measuring performance data. So to provide some background on the application, if you're in a Comcast market, you may have heard of X1 already. This is the new set-top box. It's leaps and bounds better than the other ones that you've had. And basically, X2 is a design update to that, first and foremost. And secondly, it involves storing your DVR recordings in the cloud. So this has a couple of benefits. One, you get additional space for your DVR recordings. And this also allows you to stream your DVR recordings to any device inside your home, be that a desktop, laptop, mobile phone, tablet, which is great. You can also stream live TV and on-demand content. So the idea was that we'd have a consistent experience across all these devices. So we basically split the teams up into the set-top box team, iOS, Android, and web. And I was one of the developers working on the web application for this. And essentially what we're doing is turning your web browser into a TV. And part of that experience is, you turn your TV and video is always playing. So because of that requirement of kind of video being first and foremost and always playing, we built it as a single-page web app. We used Backbone on the front end. It was a Ruby on Rails application. Talking to a hypermedia API that all the applications talked with. But what I'm going to talk about really doesn't matter if you're using Backbone or any other framework, or even if you're just building a website. These rules will apply regardless. Also, when you consider that your experience of watching TV is you turn on the television and boom, video starts playing. So obviously, you want this app to be fast, just like TV is fast. So in our quest to make it fast, we asked ourselves a few questions I'm not going to cover in this talk. So one, what do existing tools provide? What data do you care about? How do you go ahead and gather that data? And then once you have that data, what do you go ahead and do with it? Now before you can fulfill a requirement to just make your website fast, you need to know first how fast or slow your app or website currently is, and a way to consistently monitor those metrics so that when you get a target that you're shooting for, you can know that as you're doing different performance improvements, know that it's actually helping or hurting performance. All right, so let's take a look at some existing tools to start off with. One that we use often is Webpagetest.org. This was originally developed by AOL, and they ended up open sourcing it, and Google has kind of taken the reins on this, and they've done an excellent job. Provides a bunch of great data and suggestions as well for what to do with your website. You get to see an overall performance of the page on its first load, and then a repeat view when assets are cached to see what the time differences are. Give you a nice waterfall view that you can usually see in like your network tab or your performance tools, showing the detail and the timing information. Connection view shows you each individual TCP connection. So you can see how different browsers shard those. You get a nice Pagespeed Optimization check to basically tell you, hey, here's things you can do to improve performance, similar to what YSlow does. Puts it right there in your face. But here's one spot where it kind of falls short a bit. So I assure you when our app is fully loaded, it does not look like this. This is a loading screen, which, I mean, the best loading screen is no loading screen, but the fact of the matter is we do have one. And we want to get that down as short as possible. And by default, web page test will be like, okay, the onload event fired. We see the page is fully loaded, so we're going to say this is the fully loaded spot. But that's not actually the case in our application and any other one that does load additional stuff after the page is loaded. There is a way to fix this in some browsers, and I'll kind of get to that a little bit later. But that's a high-level overview of Webpagetest. Phantomos is another tool we use. It has a much cooler name. And as you can see, it is a Phantom.js-based web performance metrics collector and monitoring tool. And this is basically a tool that you would want to use in your continuous integration environment, where with each commit of your code base, you deploy your code to some development server and then run Phantomos against it. And this will spit out a ridiculous amount of performance metrics for you. It's very useful. We run it with Grunt DevPerf, which I'd recommend you check out as well. That gives you a couple of benefits. One, it's Grunt, so it's pretty easy. You just run the command, and it goes ahead and runs it. Plus, since Phantomos gives you so much data, it's kind of nice to see a smaller chunk of information that Grunt DevPerf gives you, which is this little view. This is actually in a web browser, but they have it styled to be like a terminal. But it gives you that overall kind of time to first byte on DOM ready time, various other things there. Some file information on the size, number of requests, and then warnings. And then this is broken down by each time you run it. You can kind of see these charts go up and down. So I'll give you a quick glance over at what ours looks like if the video plays well for us. Okay. So again, this is a ridiculous amount of information. I'll just touch on a few things real quick. So for one, there's smallest latency and biggest latency. That's the file with the smallest latency and the largest for the response times. From the timing section, there's time to first CSS, time to first JS, on DOM ready time are things I typically take a look at. HTML. For the JavaScript, if you're not using JS hint to catch like JS console messages, that's there. Also, if there's any JS errors, it's going to throw those as well if those pop up in the browser. For the DOM, there's a bunch of different things around different DOM queries. You can see how many of those you're doing and see if those somehow have an impact on performance. Because again, you can see that basically each one of these things that it marks is for each individual time you run the grunt task, which is nice. You can kind of tie this, anything that changes to an individual commit. Counts and sizes, you can see how body size and HTML size change, CSS size, JS size. If you're using jQuery, like most people, you can see the sizzle calls that are being used. And then again, you get this nice film strip, but kind of stuck with that same issue again, where it thinks it's done loading, but it's really not done loading. And then it spits out, basically, for all the data that populates those charts up top, you get a list of all the files that were the reasons why those numbers are where they are at in those charts there. So I definitely recommend checking that out for sure. That's Grunt DevPerf again. Come on, video, cool. And it's very useful, but it also has its limitations. For one, I can pretty much bet no one is using Phantom.js to surf your website. So I mean, it's obviously similar to Chrome in many ways, but again, there's differences there. And also, you want to know about what are users actually doing on your website. So what you really want is RUM. And I'm not talking about the booze. I'm actually talking about real user monitoring. Or this is also called real user metrics, real user measurement. The M is not important. It's the real user part that's important. And New Relic is a tool used for this. They're a sponsor here, so I'm sure they can do a better job than I can about their whole suite, but I'll touch on a few things about how we leverage them. For one, they can break up the page load times by request queuing, server time, network time, DOM processing, page rendering time. So you get a little more fine-grained view into what the application is actually doing and what the browser is doing. And again, this is all for stuff happening on your server with real users, which is the benefit you want to see there. They can instrument all of your AJAX requests, which is kind of nice. So you can get performance data around any other AJAX requests. In our case, for the loading screen, we're loading in additional data, so it's nice to get those metrics for that. You end up with these charts you can do for individual AJAX requests to, again, break down those different network times. And they also allow you to manually report page load timing data. So with that issue there with the fully loaded not actually being fully loaded, you can get around that with New Relic by basically saying, hey, here's a point in time where this is where I want to say my app is actually loaded. And send that back to New Relic, and then when it builds its charts, it can take that into account. So you get the real actual full time for your app being ready. All right, now that we discussed a few existing tools, let's talk about the data you care about. So we know we care about real users, and New Relic is useful for that, but you may not be using New Relic. And even if you are, there's some pieces I feel it's kind of best to gather yourself so you can get the raw data and really munge it and get the data you want out of it. So let's talk about a feature that both PhantomOS and New Relic rely on for instrumentation, and that is a W3C spec called navigation timing. And if you want to see what this is, basically if you open up your favorite developer console and type window.performance.timing, then you'll get this, which is basically a bunch of different timestamps that mark the different parts of your full application request. And from these, it's just a bunch of numbers there, but if you look at the illustration, the spec, it kind of gives you a nice breakdown. So you can take a look at each individual timestamp and then chart it out. So you've got unloading the previous document if one was open. There's checking HTML5 application cache, the DNS lookup, TCP handshake, and then you get to the actual request itself and the response coming back from the server. And then the various DOM events happen to build up the document, the CSS object model, that kind of stuff. And finally, the onload event fires. So that's some really useful stuff. You can really get a good glimpse into what each user experienced as far as sending the first page to them. If you kind of step back at a wider level view, you can see that basically network latency is the time from when that first app cache lookup happens to the response coming back from the server. And then there's that processing that happens between the processing all the DOM information and then firing the load event. And then those together, along with some initial unload stuff, make up that full HTTP request. So then you have all that data available to you, which is nice. But of course, we still have this problem with fully loaded not necessarily being fully loaded because that's not going to be part of that navigation timing interface. So you need to account for that loading screen time. And if we have a way to kind of mark that loading screen time being done, then you can kind of grab that calculation there for that point in time to see how long the loading screen is up so you can reduce that time. And then once you gather all that data, you can start to build some nice charts like this one that kind of show the breakdown of network latency, the processing time, splash screen time, loading screen time for that kind of things. But you really can't have one chart to be like, this is my web app performance, because there's a lot of things that could be affecting these, and you can't really represent them in one graph. So let's talk about a few of those. So for one, the user authentication state. So I'm willing to bet that for the most part, if a user is signed in your web app, there's going to be more stuff going on than if a user is not signed in. And then once they are signed in, there are different types of users. Like for example, in our application, the user may have a DVR, they may not, they may just be live streaming. They may subscribe to premium networks like HBO. There could be a bunch of parental controls they've configured, and that's going to affect what we need to do as far as returning either a TV listings grid to them or the recordings that they've set up. And if a user is not signed in, it's possible you're also doing some sort of A/B testing. So you have unauthenticated users that are then being segmented into different groups, and those could be seeing different experiences and then getting different response times. And you really need to gather all of that. Also the number of items returned. In this case, I'm kind of talking about, so for us, we're making another request to get your recordings when you load up the application. So if you have a DVR, you could have 3 things recorded. You could have 100 things recorded. You could have 1,000 things recorded. And if you have 1,000 recordings and we need to return that to you, that's going to be much slower than if you only have 2. So it's important that when you're instrumenting these AJAX requests that you take into account what is the actual contents of that response. How much is the number of items affecting the response time for that. And one piece that may be a little bit specific to us, but basically with anyone dealing with video or games at this point, is we have a Flash Swift that we drop in the page because video is so core and essential to this product. We tie the authentication in with the video players. So basically, as soon as you start loading the page, we drop this authentication Swift that typically just drop it, does this thing real quick, and then it happens. But that can bleed into that loading screen time. So that's one of the things that we like to monitor is how long does it take from the time we drop that Swift to the point where it says, okay, we've got all the data we need and we can move forward with the application. Taking a step outside of our application, here's an example from Gmail. Now, in this case, Gmail was slow at one point when these three specific factors were true. So it had to be the user had the people widget enabled, they had to be viewing Gmail on the web, and they had to open an email with a large number of participants. So as you can see there, basically, if you're just logging overall response times, then you would never know that there's this segment of users that are being affected by slowness. And it's going to be much more difficult to kind of diagnose performance issues if you're just doing these overall views of, here's my response time. So make sure you consider what other unique factors in your application may impact performance when you're thinking about web performance data. All right, so gathering the data. So as I said, we basically need a way to mark the point when the application is loaded completely so that we know at that point. Okay. And when that user is truly ready for any interaction, we need a way to mark that, essentially. So how do we do that? So back in the day, we would do something like new date, get time, get back a nice timestamp. ECMAScript 5.1 gave us date.now, which is just an easier way to get that. But now most modern browsers have an easier solution, and a better one, actually. And that is high resolution time, which sounds awesome, right? Who doesn't love high resolution things? So what is that exactly? So for one, it creates a DOM high-res timestamp. You can see this if you type window.performance.now and call that method in your console. And that provides a time with sub-millisecond accuracy measured relative from the navigation start attribute of the performance timing interface. So that's that first part in that big W3C graph there. And it's also not subject to system clock skew or adjustments because it uses a monotonically increasing clock. So let's dig a little bit into what that actually means there. So here's a quick example about why sub-milliseconds is nice. I'm going to write a quick function that marks a point in time as the start time, then just multiplies the width and the height of the window to do a quick calculation. Going to return the difference of that, run that, and we get 0. So it's like, that took no time at all to happen. If we write the same function, but use window.performance.now and go through those steps, then you get this extremely accurate time. In this case, it was 0.012 blah, blah, blah milliseconds. The spec mentions that it should be accurate to the thousandth of a millisecond. I've seen some browsers be even more accurate than that. Others, especially on Windows, are only accurate to the millisecond. But again, you get the benefit of the monotonic clock, which you may be wondering what exactly that is, which I did when I first heard about it. So for what that is, I went to the person that actually reviewed the commit in Chromium, and here's that explanation of what that means. So most systems run a daemon which regularly synchronizes the time. It is common for the clock to be tweaked a few milliseconds every 15 to 20 minutes. So at that rate, about 1% of 10-second intervals measured would be inaccurate. So now you kind of see the benefit of why that monotonic clock is a nice thing to have. So now we've got this app ready marked using this high resolution time, and now we know the actual load time of the full application. There's no math needed. The value of it is the load time up to that point. But if we wanted to kind of figure out what is the actual loading screen time, we've got a problem. Because load event end is measured in a timestamp based on the epoch back on January 1st, 1970. And we've got this app ready mark, which is based off of 0 point being a few seconds ago. So we can't even do any math to figure out what is that loading time there. Unless we go ahead and mark a load event end spot using a high resolution timestamp when the onLoad event fires. And then we can do math. But it's kind of a bummer that we need to actually go through that. And the W3C recognized this, and they're working on a new spec, which is navigation timing 2. And that basically uses the high resolution time for each of the timestamps in that performance timeline with a couple tweaks. But it's still in the draft state, so you can't use this anywhere right now, unfortunately. But there is something else, and that is user timing. And this is great for a couple of reasons. One, it allows you to get high resolution durations between not only a couple manually set user marks, but you can take one of those user marks and then do a high restoration between that and a window performance timing interface. And that's really nice. This also solves the problem of the web page test issue with it not knowing when your browser's when the app is fully loaded. This will solve that problem for the browsers that support it. So as far as browser support goes, let's talk about that. So there's the navigation timing is in pretty much all browsers except for except for Safari. IE added this in version 9. High resolution time was added to IE in version 10, and Android recently added it. Again, Safari's not in that party. And user timing has even less support. Firefox hasn't implemented it yet. I checked the bug report this morning. It was basically created in August of 2012, and no one's picked it up yet. So if you want to write some code for Firefox, this would be a great spec to implement. So this means basically we need to do a bunch of marks. We need a user timing mark. We need a high resolution mark. We need a old school timestamp mark for all these different points in time. So basically, if you go ahead and you mark a page start mark in the head of the document using all three of those marks, a load event end when the onload event fires, and then an app ready when the app is ready, you can kind of break things up in these different sections here. So there's the blue is the browsers that support navigation timing. You can get through network latency, processing, the loading screen. Red is browsers that don't support navigation timing. You can basically do like a smaller version of processing and the full application. And then you can basically, stuff in green is things you can get with any browser because it's basically after the fact, so you can use either of the timestamps to do those calculations. So on Cloud TV, we do all of this. We set these marks, we do these calculations. We also log the information about the user. We take the number of items returned by certain AJAX calls into effect, and we consider the browser as well. And we log all that data. So I went to go ahead and actually do that work. I first went to check GitHub, of course, to see if someone actually was doing that, so I can just use their work. And besides a user timing polyfill, I didn't really find anything. So with that, I decided, OK, I'll go ahead, I'll do the work. And today, actually, I'm open sourcing the library we did for this. And in the spirit of a conference at the beach, I call it Surf and Perf. So this is available right now from our GitHub page. If you go to github.com/Comcast, it's there. It's also on NPM, so if you do npm install surf and perf, all is one string, it's available there as well. And this will allow you to set all these different marks. It will also have the concept of events, which is a start and end mark, as well as additional data, such as you may want to log, again, the number of items. Custom data points, like if you want to set is user authenticated or not, and all that duration calculation is built in there for you. So it's going to handle, do you use user timing, high resolution time, or not, all for you. So real quickly, I will go through analyzing this data. So I mean, you've gone ahead now. You've got all this stuff on your logs, and it's filling it up with all this data about performance. What are you going to do with it? So we build charts like this one using Splunk. There are other tools such as Kibana and Graylog2 that you can use if you don't have Splunk. Those are open source. Now here, the y-axis is the response time. The x-axis is the time, kind of by hour. But the thing you may be wondering is, what are we actually charting in this graph? And the one thing that may pop into your head is average response time. And I would argue that you don't want to chart that, or at the very least, you don't want that to be your primary focus. Because average response times are for average products. And you're obviously not building an average product because you're here at JSConf. This is the best conference. You're building some of the best products out there. So when you think about it, if you say that your application returns a response in under a second on average, that really doesn't sound that great. You're talking about averages. You wouldn't want your web host to be up and running greatly, returning a quick response on average. You want them to always be doing that. And users want that as well. So what you should focus on is the 99th percentile. At a minimum, depending on your level of traffic, you may want to go to 99.9 or 99.99 percentile for that. And that way you get to look at what are the vast majority of your users experiencing. If you look at averages, it's going to start to mask that data. So we take our 99th percentile and we plot this for all different parts of our application. So this is an example of if the user comes in via the default, which is your recent recordings, or the grid, or if they're not authenticated, or different pages. And we break that up by network latency, processing, and response time. For recordings, you can see that more recordings lead to larger response times. So we notice this from our charts. It seems for us that the number of channels does not affect response time. And lastly, to kind of drive home the point that 99th percentile is useful. This is our auth SWIFT, which is, again, that piece of flash that we drop on the page. And here's the chart comparing that to the loading screen response time for 99th percentile. And you can see that these are pretty much in line with each other. So then we know that, OK, the worst users are having that experience because of this SWIFT. So we need to focus on that. The 95th percentile, that still looks good. It starts to kind of not be as clear as you get down to the 50th percentile. But then at average, there's really no relationship there. So if you're just looking at averages, you're not going to be able to notice that this is, in fact, a big impact on the application. So to recap, make sure you measure first at the 99th percentile. Log the network latency, processing time, and full web page request. Also log any major app-specific events with the details that you need to determine that information. And leverage those W3C performance APIs for that. You can talk to me on Twitter at JohnRiv, and once again, there's a link to the GitHub repository. Thank you.